Alrighty. Hello, everyone, and welcome to Bone Tissue. So, we're going to be talking about the functions of bones and what those functions are, what bones are made of, stuff like that. So, osteology is the study of bone. Osteo is bone, ology, study of. So, osteology, study of bone. The skeleton is made of bone, it's made of cartilage, of ligaments. Why are bones important? What do they do? They function in support, protection, movement, electrolyte balance, pH balance, and blood formation. So basically, the skeleton keeps everything in place. It keeps everything spaced out, organs spaced out. That's the support piece of it. Protection, bones protect the organs. The skull is there to protect the brain, for example. The rib cage is there to protect the heart, the lungs, all that good stuff. The skeleton, the bone tissue, it is important in movement. So muscles attached to bone. We call it actually the skeletal muscular system. But muscles, they attach to bone, they have to cross over a joint, and then that's how movement happens. We'll talk about that, not in this chapter, but in an upcoming chapter. It functions in electrolyte balance. So the skeleton specifically stores calcium and phosphorus. We need this, and we usually get this from food. If we don't get this from food, then the body is going to use that by taking it from our bone. That actually leads to osteoporosis, which is a weakened skeleton. We'll talk about that towards the end of this lecture. pH balance. So specifically when we're talking blood, the calcium and phosphorus I was just talking about, the skeleton can release some calcium phosphate into the blood to normalize its pH. So if our blood is too acidic, we add some of that base, some of that calcium phosphate, and that helps us regulate and balance our pH. And then blood formation, that happens in the bone marrow, center cavity, and long bones specifically, and we'll talk about bone marrow as well. So the skeleton, it's actually categorized into two different parts basically, so the axial skeleton and the appendicular skeleton. So the axial actually has 80 bones, and it's the body's axis. It's the body's center, so it's the darker orange. Look at the key down there at the bottom right. The axial skeleton is that darker orange shading. Again, the axis, the center, so that's the skull, the thoracic cage, so those are our ribs and our sternum. The hyoid bone, the vertebral column, the sacrum, and the coccyx. The coccyx is your tailbone. And then we have the appendicular skeleton, so that's everything else. That's 126 bones. Those are our appendages, appendicular appendages. So think pectoral girdle, upper limbs, pelvic girdle, lower limbs. Everything around the axis, basically. And that's going to be that tan color right there on the skeleton. So 80 bones in the axial, 126 bones in the appendicular, so 206 bones are in the human body. Human body is comprised of 206 bones. We also have to talk cartilage when we talk bone. So notice again the color coding down there in the bottom right. We have blue as hyaline cartilage, green as our elastic cartilage, and then red as our fibrocartilage in this skeleton. So again, hyaline is blue. Hyaline cartilage is in our wrist, our elbow, wrists, elbows, shoulders, ribs, cartilage in the nose, thyroid cartilage. All of that is blue hyaline cartilage. Trachea, all of that is our blue hyaline cartilage. Let's see, elastic, that's our green cartilage. So that's the external ear and the epiglottis. We'll talk about the epiglottis a lot in anatomy and physiology too, but it's a little flap. And fibrocartilage, red. You can't really see it that well, but it's between the vertebrae, and it's in the pubic symphysis. So the pubic symphysis is right there. Boom, boom. Okay. So shapes of bones, we have 4 different types. We have long, irregular, flat, and short. So our long bones are our humerus, radius, ulna, femur, our phalanges, so our finger bones, our metacarpals, metatarsals. When we talk long, we are talking about a skinny shaft with bulbous ends. So long means long and skinny with 2 roundish ends. So don't get those confused with short, right? Here we're talking about the shapes of the bones. So our finger bones and our toes are actually long bones, okay? Irregular, over here, B, irregular bones. Those are going to be really oddly shaped, really irregular shaped bones. Vertebra are the best example. Nothing else in the body is the same shape as our vertebra. And then C, right here, flat bones. Flat are going to be sandwich, so hard bone on the outside and the inside, and spongy bone in the middle. So hard bone, spongy bone, hard bone. We're going to talk about that a lot here coming up. And that's going to be our sternum, our skull, part of our clavicle, flat bones. And then D, our short bones. Those are going to be the wrist bones and the ankle bones. Again, short, again, does not mean size. We are only talking about shape. So you can see how a long bone and a short bone are very different. Remember, our finger bones, our toes, so our carpals, metacarpals, tarsals, our phalanges, our metacarpals, and our metatarsals. Phalanges, fingers, those are all going to be long bones. Please don't call them short bones just because they are short. Long is the shape, right? Not the length. Short is the shape, not the length. Okay. Oh, and one more thing over here. Long bones, there's a lot of mechanical advantage in terms of physics with long bones. The longer the bone is, the easier it is in lifting. So our long bones, you can also classify with the bones that we use for lifting and mechanical advantage in terms of shape, right? Shape specifically. Okay, so this is a cross section right here in a longitudinal section of a long bone. So compact bone or cortical bone, you'll also hear it as that, makes up the outer shell of our long bone. So it's going to be all around the bone. It's going to be in the center cavity, and we call that compact bone. This center cavity, so compact bone is all around the bone, right? Touches the outside, touches the inside. But in the center cavity, we have what is called a medullary cavity. So that is the part of the bone, the center cavity right there is the part of the bone that stays open so that other stuff can be inside of it, right? This cavity, the medullary cavity, is also called the marrow cavity because it houses the bone marrow. So that's this yellow stuff. So let's zoom in, boom, cross section. Yellow bone marrow right here. So let's talk about bone marrow for a second. We have yellow and we have red marrow. Yellow is in adults. It's fatty yellow bone marrow. Doesn't do a whole lot, right? Our red bone marrow is in kids predominantly. and that's our blood cell formation, right? So in adults, our red marrow is in maintenance, but in kids, it's making all of our blood cells that we need, right? So in kids, it's just functioning a lot, right? Our yellow marrow in adults, it can actually turn back into blood cell production type marrow in adults when necessary, right? Otherwise, in adults, it's just in maintenance. And red marrow is left over a little bit in the skull, a little bit in the vertebra, ribs, sternum, and then parts of the pelvis. Actually, if any marrow needs to be extracted, doctors will usually go into the part of the pelvis in the back. So in a really, really thin person, you can see dimples in the lower back, and that's kind of going to be the guiding point to get to the pelvis to extract some marrow in an adult. But anyways, yellow marrow predominantly in adults doesn't do a whole lot. It's fatty. The red marrow is what makes the blood cells, and it's really, really active in children. Okay. So that's going to be inside of that medullary or marrow cavity. On the round ends of this long bone, we have spongy bone. So spongy bone is going to be a lot looser. It's going to make the skeleton weigh a lot less, a lot lighter. And it's made up of this trabecula, which we'll talk about. The skeleton, so again, compact bones right there, spongy bone on the ends. The skeleton is going to be made up of 3/4 compact bone and 1/4 spongy bone. So 75% of our skeleton is compact, 25% is going to be spongy. The long bone's skinny shaft, so the center, the shaft is called actually a diaphysis. And then the expanded heads on both ends are called the epiphyses. So epiphyses, plural, epiphysis, singular. The proximal epiphysis is going to be the end that's closer to the body, and then the distal is going to be the one that's further away from the midline of the body, right? Larger, rounder on the ends to make a solid joint socket. We'll talk about joints in an upcoming chapter. And then the outside of the long bone is called the periosteum, the outside covering, essentially. It's a fibrous connective tissue that lines the outside of the bone. And then the inside lining is called the endosteum. So outside lining is the periosteum, inside lining is the endosteum. We have articular cartilage on the ends of the bone. It's right there. And that allows the joints to glide and slide easily against the bone. And then what else am I missing? Arteries, nutrient arteries. Okay, so blood vessels. We have blood vessels that run through the periosteum into spongy bone. So through these little holes that we'll talk about. And that allows the bone to be really, really vascular. So connective tissues, our tendons or ligaments or cartilage, they are not vascular. We call those avascular. So A means not. Connective tissue, tendons, ligaments, cartilage are not vascular. They're avascular. So bones being vascular, actually, in terms of stress, it's actually, or fractures, it's better to break a bone because it's vascular. It'll heal a lot faster with blood vessels, bringing in nutrients and removing damaged cells than it is to have any sort of damage to tendons, ligaments, and cartilage. They're not vascular, right? Bones are going to heal a lot faster and a lot more easily because they have these blood vessels bringing good stuff in and taking bad stuff out. And then we have this oh my goodness. The epiphyseal line. I don't know why that's hard for me to say right now. Epiphyseal line or plate that is where the growth plate was. So this is an adult bone. Here, upcoming slide, you'll see a bone that's growing, and you'll kind of see that line or that growth plate. But in this adult bone, it just signifies where that growth plate was. In kids, there's going to be a pretty big gap, and that indicates that the bone is still growing. Here, we have fused together into this epiphyseal line. Okay. So an osteon. So this is a fundamental functional unit of compact bone that we call a Haversian system. So this right here, that's an osteon or a Haversian system. Haversian system. So here in this Haversian system, we have this little canal, a central canal called a Haversian canal. And that is what our blood vessels go through. So this little hole, this little channel is a central canal, a Haversian canal, and if you zoom out a little bit, it's part of an osteon or a Haversian system. When you see these vessels, the yellow indicates a nerve, the red indicates an artery, and then the blue indicates a vein, and they are all going through this Haversian canal, this little channel. We also have perforating or Volkmann's canals, these horizontal canals, and they're diagonal passageways that connect the Haversian canals of different osteons. So the Haversian canals, think of them as the main highway, and then the Volkmann's or the perforating canals are the side streets that connect the main highways. All right, so then let's look down here. So the rings around these canals are called lamella, and they look like tree rings. So you can remember lamella are tree rings. Lacuna, so you remember lacuna from a previous lecture, these little holes, they are these tiny, tiny little holes, and they are in the small spaces between the lamella. And then inside the lacuna, we actually have our bone cells called our osteocytes. So inside the lacuna are our osteocytes. So let's see. We also have these tiny little canals here, the canaliculi, and they actually connect each lamella, so they help everything communicate. There are connection pieces like our Volkmann's canals were, right? But they're the canaliculi between the lamella. And there's small channels going in all directions from the lacuna to aid in communication and connection. So everything's communicating, right? We have communication within the ring, between the ring, within the canals, between the spongy bone, and between the compact bone, which allows us to bring all these nutrients in and wastes out. A lot of communication happening here. Again, the lamella are the tree rings. Lacuna are the little holes where you can see the osteocytes, and then the canaliculi are the little channels that connect all of that. Osteon is our Haversian system. The Haversian canal is a little channel that allows the vessels and nerves to go through. We've got compact bone, spongy bone, all of these little winding things in the spongy bone are called trabecula. We have our little side streets, our Volkmann's canals or perforating canals that allow vessels through and communication between the spongy bone and the compact bone. Go to the next slide. All right, so this is what that looks like. Compact bone, spongy bone. We just call it spongy. And compact bone is a sandwich. So if we were to get hit by something, typically only the outside would fracture. Spongy bone would take some impact, but we would never get to the other compact bone lining the inside. And we'll talk about that more. And then spongy bone, if you zoom in, is made up of these trabecula or trabeculae. I say trabecula. Okay, moving on. All right, ossification, process by which bone is formed, aka bone formation. So this starts before you're born and it continues as you grow and repair your bones throughout your life. So we have two different types. We have endochondral ossification and intramembranous ossification. Again, ossification, bone formation. So first, endochondral, let's break that up. Endo, inside, chondral, cartilage. So what this means is it's cartilage first, and then bone is laid on it. It proceeds through cartilage. It's constant. It's important in formation of long bones. It takes longer here to form a bone, and it stops at 2 years old. So this is constantly happening till you're 2 years old and then stops. Intramembranous, so this is development of bony tissue inside mesenchymal tissue. What is that? You've never seen that before? It's embryonic tissue. Okay, so this is without making cartilage first. So there's no intermediate cartilage stage here. This one is a little bit faster. It's super important in formation of flat bones, so your skull, your sternum, ends of clavicles. And it takes less time to form a bone here, but it stops at year 18 in females and 21 in males. So we just said that endochondral is constant and stops at 2 years old. So how is intramembranous? How is that faster but stops at year 18 in females and age 21 or year 21 in males? So it's not constant, right? Intramembranous. But think about your skull growing. If your skull was to grow super, super fast and stops at 2 years old, you'd have a huge head, right? There would be no sort of balance there. A huge, huge head and a tiny little body. That doesn't make sense. Okay, so your skull, all in all, takes less time to actually grow to get to the size that it needs to be, but it's going to happen more slowly throughout your life, right? So it's going to grow faster, but it's going to grow in stages throughout your life. And it's going to stop growing when you're 18 years old in females, 21 years old in males. Whereas endochondral is constant growth that first starts as cartilage, then bone is laid on top. And it's going to take longer to form that bone, and it's going to stop at 2 years old. So know the difference there, okay? So it takes longer time, stops at year 2, takes less time, stops at year 18 years old and 21 years old. That says stops. Oops. Add a T. Stops. Okay. So know the difference. And we're going to talk about each. So intramembranous ossification produces flat bones of skull, clavicle. So think of a sonogram. You see the head of a baby pretty easily. The skull forms really fast. You have to protect the brain, right? That's intramembranous ossification. So the easy way to remember is first you have a membrane, osteoblasts form, matrix hardens, spongy bone forms, compact bone develops. So a central area begins to form osteoblast. Blast is the cell that a tissue comes from. Bone comes from osteoblasts. So then the fully formed cells are called osteocytes. Later in life, you have osteoclasts that break bone down, but we're not talking about that right now. We are talking about osteoblasts that build bone up, and that's what's happening here. We are developing spongy bone. Trabecula are the tiny little crossbeams that form that supportive framework of spongy bone. It's loose, it's light, there's plenty of blood flow. So on the outside here, we have compact bone from both sides. So it's a sandwich of compact bone, spongy bone, compact bone. Think about getting hit in the head. Spongy takes the impact, cracks the outside, but it doesn't go all the way through to the inside compact bone. And that's intramembranous ossification. So endochondral ossification is what's happening to the rest of our bones. So we have cartilage first, bone forming in the center, cartilage in the middle starts breaking down, blood vessels and osteoblasts move in, and then we are here in stage 4. The middle grows out, so the middle here is growing out, the ends are growing in, and then they are growing, boom, together. And the growth plate, right here, the epiphyseal plate, you can easily see. And then you can see the spaces there where that epiphyseal plate is coming together. Okay. Quick and easy explanation. All right, so here we have a normal bone versus a bone that's got osteoporosis. So here we're getting into bone disorders. So there is a law called Wolff's Law that states that bone adapts to the stress that you put on it. So if you use it, it strengthens. If you ignore it, it weakens. So in osteoporosis, that's loss of bone mass and bone density. So here bone is reabsorbed faster than reformed. So our osteoblasts are losing the battle with our osteoclasts. So here, although the trabecula are hard, they're brittle and they shatter. This can be things like age, not using it, it's weakening, right? Or nutrition, you're not getting that calcium and phosphorus from your food, so your body is taking it from your blood. Your osteoclasts are winning, and osteoblasts are not building the bone that fast enough, right? We're losing it faster than we're making it. We also have something called osteopenia. It looks like normal bone, but it's super soft, and it's like powder. It crumbles apart, and bones break pretty easily in osteopenia. We also have osteoitis deformans, which is Paget's disease. Paget's disease is similar to brittle bone disease, osteogenesis imperfecta, and those are also linked to osteoblasts and osteoclasts. In Paget's disease, bone is taken away and reformed in the wrong places, so we're making bone in the wrong spots. It's abnormal bone remodeling. And then in brittle bone disease, we have super thin bones, and those bones shatter very frequently. We have frequent fractures in brittle bone disease from minor stress. So just, hitting the door on the way out by accident can cause a bone to break in brittle bone disease. And then here we have some fractures. Know these different types. So a transverse fracture is just a clean horizontal break. It's a break straight across the bone. It can be non-displaced. So you can see here, the bone is still together. It's not displaced. Or it can be displaced where the bone moves apart from itself. Any of these can be displaced, right? Except for green stick, which we'll get to. So non-displaced, we're still in alignment. Displaced, we're out of alignment. Transverse break is a clean break straight across the bone. A compound fracture is also known as an open fracture. This one's pretty intense. This is called a compound or open fracture anytime the bone pokes through the skin. So there are sharp edges here, tissues get cut, bone slivers are in the tissue. They can kind of keep coming out of the tissue. So this one's pretty intense, definitely requires surgery. Oblique, this one is also called a spiral fracture. So right here, oblique fracture, spiral fracture. This happens when the bone is twisted apart. It's easy to displace. It's not in line anymore. And on these, you are not allowed to put any weight on it at all so that it doesn't easily displace. Comminuted right here, that's a crush. So something happened that crushed the bone. Here, surgery is 1,000% required. Typically, surgeons will fill in this crush with some bone glue, this like bony matrix that helps in healing and hardening. Then we have a green stick fracture, which is a break only on one side. So this is when the bone bends and cracks on one side only, doesn't go all the way through. Pretty common in kids, and it's a lot milder than any of the other breaks we just looked at. And again, any of these can be displaced except green stick because the break doesn't go all the way through in green stick. We also have stress fractures. We call stress fractures hairline fractures usually. And this happens from tiny cracks in the bone from repeated stress. You're doing the same thing over and over again. There's not a single big impact that causes stress fracture or hairline fracture. Think of runners that are just doing the same impact all the time. They can get a stress fracture. Ballet dancers, ballerinas, they can easily get stress fractures or hairline fractures. We also, I want you to know pathological fractures. These happen from things like bone cancer. So weakened bones are weakened because of that bone cancer, which can lead to pathological fractures. And then lastly, we have these 2 short videos. So I can talk to you about osteoporosis all day, but watch this YouTube video. It's less than 5 minutes long, so you can see what actually happens here. And then we also have a quick little bone growth animation video, so you can kind of see how the bones grow. So check those 2 videos out, and watch this video over a couple times. Take some notes, because these are not going to be things that you've heard of over and over again. And that's it for bone tissues.